Hello again. In this short video, we're going to look into how to implement a logic function using NAND gates. Before we go in, I want to share two important properties here in circuit design. We talked in the last video that when we have a NAND gate, when we connect the two inputs together, this operates the same as a simple inverter. So basically, when you can implement an inverter using a two-input NAND by connecting the two inputs together. That is one property. And number two is when you have an inverter F, for example with input F, and when you have two inverters back to back, this input F becomes F bar and input F bar becomes F double bar. This is nothing but F. So basically, when you have something like two inverters back to back, this can be replaced by a simple straight line. We have to remember these two properties and when we simplify the circuit. And before we go in, I want to do one other thing. For simplicity, we are not going to represent the inverter with the whole inverter symbol, but we're just going to represent it by a small bubble. So whenever we have two inverters back to back like this, it can be represented by a simple straight line. Just remember that. So now let's see here. We have the function f equals a plus bar b. So how do we implement using NAND gates? First of all, I would say implement the function using just the AND and OR gates that you're most familiar with. So we have to have a plus a bar b. So first of all, I have to implement a bar. So I have a becomes a bar and multiplied by one term, that becomes b, a bar plus b. Now add it to a. That becomes f, right? We all know that. So how do we start? The next step is to see, okay, since we know we can convert all the inverters to NAND gates using the model here, we can keep that to the last step. Now let's see here. How do we change this circuit to NAND gate? First, start with step 1. Focus on the AND gates and convert that to a NAND. So what I'm going to do here is we have an AND gate here. By can we add an inverter here? That becomes an AND gate. This whole becomes an AND gate, right? But the whole logic changes. So what I'm going to do is I'm going to add one more inverter here. One more inverter here. So that way, whatever the output comes here, the same output goes here. Because remember, when we have two inverters back to back, that can be replaced by a single wire. So earlier there was a single wire. I put two inverters there together, so the logic function doesn't change. Now, the next thing is, okay, we added a logic here, and so we need to add, in order to retain the logic, we need to add one other inverter here. Now, if we add one other inverter here, we need to add one other inverter here as well to make sure the logic doesn't change. So basically, I have a coming down here, and this becomes a bar, right? So, but if you see, you have a bar here, going from a to a bar, and this inverter is also doing the same thing. So basically, I'm going to delete that inverter and take the circuit, connect it from there. So end of the day, you would have a circuit that looks something like this. A, B. So now let's see here. Is this a NAND gate? Yes, it is a NAND gate. Is this a NAND gate? Actually, it is a NAND gate, because if you remember this function, let's look into this. If I say this is A, this is B, what we're doing here is A bar plus B bar. And as we remember, A bar plus B bar is AB whole bar by De Morgan's law. So this is a NAND gate by itself. So we are good here, we are good here, and the last one is we need to change this inverter to a NAND gate. So basically, change that to a NAND gate and replace everything else So I have A, I have B, and this is F. So we have a NAND gate here, I have a NAND gate here, I have a NAND gate here. That's it. So step 1 is focus on the AND gates and convert them to NAND gates. Step 2, focus on the OR gates and convert them to NAND gates. And we're going to look into a little more complex problems on NAND gate implementation during class. Thank you.